Hello everybody, my name is Ethan. Welcome back to the channel where today we are hopping back into the machine learning course on Codecademy. In today's video we are doing concurrent programming. We're going to have a lot to go through today with concurrent programming. In the previous video we finished the Learn Git module. So we finished with the GitHub workflow. That ended up being really nice, so we enjoyed that very much. In this section of software engineering in Python part 2, there was a section that's called exceptions. So if you are unfamiliar with what exceptions are inside of Python, that's something you might want to review somewhere else because I'm not going to use a video to cover it. This was already completed for me, so we'd be going over content that I did 9 months ago, and I don't really want to do that. So instead, we are going to continue on with concurrent programming. Again, if you missed the GitHub work video, here it is on my channel. There is about, I want to say, 3 videos on Git and GitHub, so if you missed any of that, be sure to go check it out. So concurrent programming, let's learn about concurrent programming. In this article, we're going to talk about the following topics: sequential programming, concurrency and parallelism, asynchronous programming, threading, multiprocessing, and asynco modules, kind of what it sounds like. Asynco, maybe? I actually am not sure. Asyncio Pro. We always start off the video with something like this. Let's see. Oh, it was right at the top here.
Asyncio.
Asyncio. So threading, multiprocessing, and asyncio modules. All right, sequential programming. As you have gone along in your Python journey, you most likely worked with sequential programs. These are programs that follow a set of instructions. We can view this in the following diagram. So we have begin, statement 1, statement 2, statement 3, and then end, right? Sequential. For example, if we have the following program for I in range 4, print I, end program, we will see the numbers 0 through 3 printed in order as the program follows the sequence of events. Great, we have a deterministic algorithm that suits our needs. However, in this program, we have 4 steps that do not take a long time. Let's imagine we are a data scientist working on a complex learning module or a backend developer with some extensive database. Suddenly, we are dealing with many more steps that take a lot more processing power. In situations like this, the concepts of concurrent programming and parallel programming come into play. To give us a basic intuition behind each of these paradigms, let's picture 3 separate scenarios in ordering food at a deli. Analogies. We can view sequential programming as a line of customers with access to one register. In this scenario, each customer has to wait a single file line until they can make their order. This is fine if there are only a few customers. However, as the number of customers piles up, this can be incredibly inefficient for the deli. We can view the concurrent programming as multiple lines of customers with access to one register. In this model, we might have 3 separate lines. The cashier can pick one of the customers who is ready to order from the front of the line. This can speed up ordering for the deli, as if a customer decides they are not quite ready to order yet, they can let one of the other people in front go ahead. And we can also view parallel programming as multiple lines of customers with access to multiple registers. In this model, there are multiple registers that can divvy up the customers. This way, the deli is more likely to avoid long lines and run a more efficient operation. Finally, we also have asynchronous programs. If we add this paradigm to our analogy, we can view it as having a wait queue where each customer has a ticket. Once a customer's food is ready, their ticket is called. However, the tickets don't necessarily get called in order. Instead, any ticket can be called once the customer's food is ready. Sequential, synchronous, would mean that customers would have to wait for each other before they get their food. Or wait for each customer before they get their food. Defining technical terms. Now that we have some high-level understanding of these concepts, let's get back to programming mode and develop technical definitions for these terms. Concurrency is the process in which we have multiple tasks running and completing during overlapping periods of time. Parallelism is the process in which we simultaneously have multiple tasks or separate parts of the same task running using multiple CPUs, core processing units. These definitions seem quite similar. However, we should identify some key differences between the 2 processes. Parallelism needs hardware with multiple processing units, whereas concurrency only utilizes one. Concurrency requires at least 2 tasks to exist, whereas parallelism only requires 1. Parallelism assigns each task for a core to execute, whereas concurrency executes all tasks by switching tasks simultaneously. And finally, parallelism means we can do multiple things at once, while concurrency means we can juggle between tasks. So processing unit with just 1, we might switch in between tasks. If we had 3 processing units, we can do all of them at the same time. These diagrams should remind us how our deli line analogy from before. Think of each processing unit as a register and each task as a line. With 1 core, we can split up the task cleverly to speed up the runtime, but with multiple cores, we can run those tasks at the same time, right? All right, methods in Python. We're going to cover the following libraries: threading, multiprocessing, and asyncio. I think I'm still saying that right. Using these, we can create concurrent, parallel, and asynchronous programs that are much faster than synchronous ones. We can map these libraries one-to-one as threading to concurrency, multiprocessing to parallelism, and asyncio to asynchronous. In the next few lessons, you'll learn about the concepts of threads and processes, and there will be concepts to create powerful and efficient programs to see our conceptual understanding of concurrency, parallelism, and asynchronous programming come to life. I wonder how many times I'll say those 3 words in this video today. All right, introduction to processes. When using a computer, multiple programs can often be found running the same time, perhaps one for playing music, another for creating documents, just like I am right now. And also, I'm going to be glowing throughout this entire video. That's just what it's going to be. I don't know why. I tried fixing the camera. It's not going to work, so we're just going to continue on. But for example, in this video, I have the website for Codecademy up in the window that you see, but I also have my recording software up. So that's something where we have multiple processes up, right? And when a program is executed, these processes are not only central for usability of a computer, but they are building blocks of an operating system. Cool. All of the processes running on your computer can be found in the process manager, task manager, activity monitor, and system monitor, right? On the different systems there. Okay, life cycle of a process. To best optimize the performance of processes and their priority changes as they wait for access to a limited resource, processes are put in one of 5 states: new, ready, running, and blocked. So, new is the program has been started and waits to be added to memory in order to become a full process. Ready, process fully initialized, loaded into memory, and waited to be picked up by the processor. Running, currently being executed by the processor. Blocked, the process requires a contested resource that it must wait for. Finish, the process has been completed. This life cycle, the life cycle of a process is its journey between the 5 states, beginning with new and ending with finished. As CPU cores traditionally only executed 1 task at a time, managing the state of processes allows the processor to interleave these tasks and allow multiple processes to best share these cores and other limited computer resources. For example, instead of a process occupying the processor while waiting for user input, it can be marked as blocked to have that processor focus on another process in the ready state until that input arrives. Blocking isn't inherently negative, as some tasks require more. Marking these processes as blocked allows the processor to prioritize other tasks, creating a more responsive and efficient system. Similarly, some processes may also be reverted to the ready state through preemption, where tasks are temporarily interrupted by an external scheduler for urgent reasons, such as a hardware interrupt signal asking the system to shut down. All these switching processes do come with overhead that is best to be avoided. This is called context switching and is typically an expensive operation, as the current state of the processes need to be stored and then reloaded to resume execution. How could the block state be further broken down to be more descriptive? Right? Process layout and process control block. When a process is initialized, its layout within memory has 4 distinct sections: a text section for the compiled code, a data section for the initialized variables, a stack for local variables defined within functions, and a heap for dynamic memory allocation. Processes are also initialized with a process control block that is required by operating system for managing the process. Just a lot of information about how processes work, and this is what it looks like. Cool. Introduction to threads. While a process is an abstract data structure that represents all of the necessary information to run a program, a thread represents the actual sequence of a processor instructions that are being actively executed. Each process contains at least one thread to be able to execute, although more can be created to allow for concurrent processing if it's supported by the CPU. These threads live within processes within the process and share all of the common resources available, such as memory pages, active files, as shown in the image to the right. These shared resources are critical for the definition of a thread. While each process is typically independent, multiple threads usually work together within the context of a process. By sharing data directly, there is faster communication and context switching between threads than what is possible for processes, all while taking fewer system resources. For example, within a video game process, multiple threads may exist to manage separate services relating to the operation of the game, collecting user inputs, and another for producing sounds. All these threads live within the same process. They can easily share information about the game, such as the type of ground the player is walking on. This can be used to affect both the speed of the character moves and the input thread, as well as the noises created by the sound thread. Boom, boom, boom. Multi-threading. Typically, a single CPU core can only execute one thread, and therefore one process at a time. With a clever use of blocking context switching, this limitation can be obscured through users' nanosecond-long pauses that allow processors to be completed near simultaneously. With some hardware's advances, single CPU cores now execute multiple threads at once, which is a capability called multi-threading. Computations have a variety of benefits, such as improved system utilization and system responsiveness. This is because tasks can be more evenly split between multiple threads, exhausting all available computing resources and allowing longer tasks to run in the background separate from user input. The image to the right shows how threads share data to achieve this. However, these optimizations come with disadvantages due to the additional complexity required for the implementation. Not only are these programs more difficult to write because of their non-sequential nature, but they also create a whole new class of bugs. The two most common examples are data races, where multiple threads attempt to modify the same piece of data, and deadlocks, where multiple threads all attempt to wait for each other and freeze the system. Also, since these bugs are usually related to the tight timing of CPU interactions, the program can be considered non-deterministic and therefore untestable, compounding the problem. So, we have multiple threads here, local data, all gets shared, all takes access of the shared data, right? Kernel threads versus user threads. Threads can behave differently depending on the environment they are created in. A thread built into the existing process is considered a kernel thread. This means that the kernel within the operating system is fully aware of these threads and directly manages their execution. There are also user threads that exist solely in user space and, while functionally identical, are not known or controlled by the kernel. This allows for more fine-grained control by developers. These threads are even more difficult than their kernel counterparts, as they save on the costly indirection of making a system call to constantly interact with the kernel. While these user threads typically operate independently of the kernel, they do need to be mapped to the existing kernel threads in order to have the operating system execute them. There are three common models for mapping user threads to user kernel threads, as shown in the image of the right. 1.1, kernel level threading for a simple implementation that best follows the hardware acceleration provided by the kernel threads. And 1, user level threading for ultralight threads that can quickly communicate and context switch, but do not benefit from hardware acceleration due to the sharing the same kernel thread. And MN hybrid threading to get the best of both of the above solutions, very light and fast threads that can be hardware accelerated as necessary. However, this complex implementation can lead to bugs such as priority inversion, where less important tasks are mistakenly prioritized. Review and wrap up. Congratulations, you've finished learning about some of the key foundations of an operating system, the processes and threads, and all other code that the system rests upon. A process is an abstraction within the operating system that represents the program while it's in execution. These processes exist in 5 states that are leveraged to allow CPU cores to alternate between ready and blocked processes to best take advantage of limited computing resources. A thread represents the actual the actual sequence of processor instructions that are being actively executed. Each process contains at least one thread and can contain many such structures that all share resources among each other to allow for faster communication. This all allows them to be lighter and require fewer system resources. With the hardware advancement of multi-threading, individual cores can also execute multiple threads at once, further improving system utilization and responsiveness by more effectively splitting up tasks. Threads behave differently depending on the environment they were created in. Kernel threads are constructed through system called kernel, while user threads are constructed using local function calls. Again, I don't know why I'm absolutely glowing today. I have my window completely shut, so we're going to just keep going here. What is the difference between a computer program and a process? A computer program is a collection of of instructions stored on the disk, while a process is required by the operating system to identify and control a program. A program is a collection of instructions stored on the disk, while a process is an abstraction used to represent the program while it's executing. I like this one the most, just because that is exactly the textbook definition of a process. Within memory, the layout of a process has 4 distinct sections: a text section, a compiled code, data section, a stack section, and a blah, 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 blah. It's going to be a heap, right? We got to have a heap of dynamic memory allocation, right? What is the purpose of the process control block? To organize the layout of the process in memory, to represent the sequence of program instructions that are for the operations, to move the process between its 5 possible states. Probably this one. For operating system to identify and control the process. Each process is initialized with a process control block that is required by the operating system to be able to identify and control the process. Process blocked. What is a parent-child relationship between processes? When 2 processes happen to share the same state within the, not just another process. Multi-threading allows for more compact control. Multi-threading allows CPUs to alternate between running and block states to take advantage. Yeah. Oh, what? Multi-threading allows for CPU to execute. Oops. We might end up having to do this one again. We'll see, though. What is the downside of multi-threading? Requires extra data. Can create more complex code due to manage resources and non-determinism brought by synchronizing many concurrent threads. Multi-threading disallows the usual. It's this one. What is a thread? A thread is an abstraction used to represent a program while it's executing. No, is a collection of instructions. A thread represents the sequential program instructions that are actually being executed. A thread represents the layout of process 4 distinct sections. Yeah. What is the difference between a kernel and user threads? Kernel cannot be blocked. User threads can be preempted, but kernel threads cannot because they are too high priority. Kernel threads are constructed through system called kernel. Yep. How does an operating system attempt to take best advantage of limited computing resources? Context switching between ready and blocked. Yep. When is a process blocked? When a process has to wait for a contested, yeah. What is preemption? Attempting to predict the result of a conditional statement to speed up processing when a process is temporarily interrupted by an external load. Yep. All right, so we missed a couple here. Let's go to the ones that we missed. Question 3 we missed, and it was, what is the purpose of a process control block? And the purpose of it is it's for the operating system to identify and control the processes, and there's the reasoning, right? Number 6, we also ended up missing. Multi-threading. What is the benefit of multi-threading? I thought it allows CPU cores to alternate between ready and blocked processes, but it's actually allows a single CPU core to execute. Yeah, I guess I should have seen allows CPU cores multiple, but a single CPU core to execute multiple threads, right? We're going to continue on here with concurrent programming and actually do some stuff now. this is perfect because now we're going to be able to get into some actual content here. So far we've seen what concurrent programming is and learned about the processes and threads. Now we're going to apply our knowledge to these concepts using Python. In this lesson we're going to learn about 3 modules: threading, asyncio, and multiprocessing. These modules can help speed up programs that provide design clarity. Alright, much of this lesson will involve comparing the efficiency and behavioral sequential programming with concurrent programming. You should see a sequential program with a timer. We'll use timers throughout this lesson to track how long the program takes. So it looks like it took just about 2 seconds for the thing to say hello. Oops. The threading module. In the previous lesson, we saw what a thread is. Let's see how we can speed up our Python programs with threading module. To review, a thread is a unique flow of execution. Theoretically, multiple threads mean the ability to run multiple things at the same time. However, in Python, threads do not actually run simultaneously. They merely appear to do so. Still, we will find that threading can increase the speed of our program. Generally, threading will perform much better than sequential programming if tasks within your program spend a lot of time waiting for external events to happen. To create a thread instance, we will use the following code: import threading, and then example thread is equal to threading.thread, and then we'll say target equals some function, arguments equals some arguments. There are, excuse me, 2 main parameters. Target, this is the function where you execute with threads. It defaults to none. And args, this is the argument or set of arguments applied to the target function as a tuple, and it returns or defaults to none. For example, let's say we wanted to apply a thread to the function analyze list with the arguments list1, list2, list3. We'll use the following argument or code. T is equal to threading.thread, target equals analyze list, args is equal to list1, 2, and 3. After creating our list instance, we also have to start our thread using .start. Therefore, make sure T executes on run when we write. To make sure T executes on run, we write this, t.start. Let's practice with an example. Let's apply a thread to the sequential example from our previous exercise. In script.py, we have a function called greeting with sleep right here. To start, call greeting with sleep with Codecademy as the input inside the terminal. Okay, so we're just going to do a very simple function call here where we do greeting with sleep, and we're going to put code Codecademy as the input. And then inside this terminal, we'll do Python 3 script.py. Oh, oops. Python 3 script.py. And it prints Codecademy. And it took 2 seconds to load, right? Let's try running greeting with sleep with a single thread. Create a thread object called T. So I'm going to move this down now, and I'm going to put T is equal to threading.thread, and we'll say that the target equals, and we want to use greeting with sleep, right? Okay, I'm going to get rid of this one. Actually, I'm just going to comment it out. Oh, we have to remember to do t.start. Oh boy. But 10. see what I was doing wrong. Oh, this is interesting. Okay, that worked. Interesting that we had to put the comma in. I'm pretty intrigued by that. Cool. Using multiple threads. Is it going along here? Oh yeah, it is. Never mind. We have seen how to create a thread in Python. However, we didn't see any speed or efficiency benefits in our previous example. To see the benefits of threading, let's learn how to create multiple threads and test them in our example. When creating multiple threads throughout the course, we will use one of the following approaches. Right, create each thread, start each thread, or create a list of threads and start each thread. The benefit of the second approach is that it keeps track of our threads in a list called threads. In the next exercise, we will see why it's helpful. Therefore, we'll follow the approach going forward, where we make a list of threads. In script.py, we have some code set up for you. Greeting with sleep is loaded in. However, this time it does not have the timer code. Instead, a function called main threading contains the timer code. In this function, we'll write a code to initiate 4 threads. What's the question? Okay. So it says inside of main threading, so it wants us to go through greetings as okay, so then for I, we'll say t is equal to threading dot thread with the target of greeting with sleep, and then arguments is gonna just be greetings at the I, right? And then I'll put in that comma because I'm unsure. And then start the created thread. So does it want me to creating a threads list? Yeah, no, it doesn't. It just wants you to start. Finally, call main threading. Put that down here, main. Okay. Python 3.script.py. Wow, it went very quick. Something similar. Is mine faster than theirs? Nope, theirs is faster than mine. Damn it! You'll explore. Input. Just click check work. All right, joining a thread. In the previous exercise, we started working with multiple threads and noticed that some interesting behavior. We'll investigate this behavior more with the .join threading method. We can use .join to tell one thread to wait for this thread to stop before moving on. Let's see how to implement this and try it out on our previous example. We'll use .join after each thread has already been initiated. see. So obviously initiate 3 threads. With the approach from the devious exercise, we do .join. We do 14 threads. The second approach is much easier for keeping track of all of our threads and much more efficient if we have numerous. In script.py, the code has been loaded in, is almost identical to the final code you had in the previous exercise, but a empty list called threads has been added to main threading. Within the for loop beneath hashtag add append code, so to use that thread threads dot append t. So we'll do that, Python 3 script.py. Okay, underneath add join code here, write a for loop that traverses threads, for t in threads, t.join. Okay, just going to do the same, Python 3 script.py. Okay, so let's walk through this. Now that we're using .join, main threading does not complete until the thread has been executed. Therefore, we got a more accurate measurement of 2 seconds. If you were to run this with sequential programming, it would take 8 seconds, since calling would run into time.sleep 2 4 times. Why the output order is the names and then the greeting hello. This is because when each thread is blocked by time sleep 2, they begin to work concurrently to complete each task. In the next checkpoint, we'll see some interesting behavior resulting from this concurrency. Check work. Change the following statement of print says hello to print string plus space says hello. Wants me to make a prediction. I ain't got time for that shit though. Cool. The asyncio model. Sorry. Now we'll cover another concurrent programming model, the asyncio model. The asyncio model uses async/await syntax. Async and await are 2 keywords that allow you to build and execute asynchronous code in your programs. The async keyword declares a function as coroutine. Coroutines are functions that may return normally with a value or may suspend themselves internally and return a continuation. This is a fancy way of saying they allow tasks to be paused and resumed to mimic multitasking. This is conceptually very similar to what we saw with threads. Coroutines are at the heart of asynchronous programs in Python. The await keyword suspends execution of the current task until whatever is being awaited on is completed. For example, if we have an await function task 2 with coroutine task 1, this tells suspend task 1 until task 2 is complete. Let's apply this to some real examples and see how we declare asynchronous functions in Python. The following code block defines hello async, prints hello, waits 3 seconds, and prints how are you. So async define hello, print wait, how are you. To continue the coroutine, we have to use the following syntax. Loop is equal to async get event loop, run until complete async. Okay. Note this has been updated as of Python 3.7 is now asyncio.run. Okay. We'll have to use the following, use the longer syntax in this lesson, and in future projects do the Python. I apologize for this inconvenience. Let's change greeting with sleep async to an asynchronous function. To do this, add the async keyword. So we add in front here, we add async See, I thought that was going to happen. It's probably... Oh my god. A yo sleep. Okay. Use 2 lines of loop syntax noted in this lesson to run your asynchronous call your function string set equal to. What do you think the output would be? So we want to use the loop. Create a new loop. Cool. Multiple asynchronous tasks. We use our knowledge of async/await syntax to do some complicated tasks. If we wanted to run multiple tasks, we can do a setup that is similar to how we created multiple threads. Let's walk through the following code. We define main as a coroutine function. Tasks is a list of separate function calls. Okay. Inside of main async, below your this, I assume we're going to write some code. The gather to group tasks and greetings. All our tasks together allows them to be run concurrently. You can read more about it here. It is giving me await syntax. Okay, so we do await async dot gather. I don't get what the star is for. Tasks, which in this case would be what, star greetings. Call your main async function. Oh. We gotta do loop. Ace dot it's not just dot loop, it's get event loop. Perfect. And then loop dot run until complete. And then we'll put the variable doesn't have a string, so we can just do Yeah. I did, yeah. I did change it from print says hello to print string. I guess we can check it here, see if I did do that. Maybe it changed, who knows? That time it worked, who knows? Okay, the multiprocessing module. We are onto our final Python module, multiprocessing. This module is unique from threading and asyncio in that it allows users to leverage multiple processors on a given machine simultaneously. This is because instead of threads or asynchronous tasks, multiprocessing is powered by sub-processes. Implementation will look very similar to how we approach the threading model. We went over processes in the previous lesson. We're now going to implement them in Python. To create a process in Python, we do the following. Cool, very similar to the threading module. As the arguments are identical, target is the function we execute. Also identical is this threading module with the start process. We use p.start. Start with an example. Let's run greeting.sleep. So we'll say process is equal to multiprocessing dot process targets equal to this case would be greeting with sleep. Args is equal to a tuple of the arguments. What is we want the arguments to be? Codecademy is the argument. Codecademy. We can now run it by doing Python 3 script no py. Very nice. Forgot to add that comma. Very cool. Using multiple processes, we have seen how to create processes in Python. However, we didn't see any speed or efficiency benefits from our previous example. To see the benefits of processes, let's learn how to create multiple processes and test them out in our example. We'll create multi-processes using one of the following approaches. Either a list or list comprehension. For the rest of the lesson, we'll use the first approach. We may ask you to use the later approach, right? All right, we have some code set up for you. Greeting with sleep is loaded in. However, this time it does not have the timer code. Instead, a function called main processing contains the timer code. In this function, you will create and initiate 4 processes. Okay, so it wants me to, inside this loop, say for I in range length greetings. We'll say P is equal to multiprocessing dot process with target equal to I assume it would be the greeting with sleep function. Yep, greeting with sleep function, and takes one greeting from greeting at each iteration. Okay, so args is equal to the tuple of greetings at the index of I. We'll add the comma. Then we'll do add process to the process list and start to create a process. So we do p dot or processes dot append p, and then we'll do p dot create a second loop for key in processes p dot join. We've called main multiprocessing, so now we should be able to just do Python 3 script.py. Perfect. You should see something like the following. That's exactly what we see. Change the following print statement from says hello to string plus. We can now run Python 3 script.py again. And we'll see this time says hello. Awesome. Review. Congrats on making it through the concurrent programming lesson in Python. We have covered creating a thread, joining and creating multiple threads, using async, and creating and joining processes. Right. Fill in the code to create and start a thread with the following. The target is some function. The args are list 1, list 2, and list 3. Import threading. T.start. Threading is they can help. I didn't talk about that. Well, no, I don't know if I can actually even get this correct now. To create multiple processes in Python using list comprehension. Oh my mother. Okay. Got the first one wrong, or second one wrong there. We'll probably have a project if I had to guess. Yeah, concurrent programming. There are 6 functions already defined in this code. There's a solution as well here. Cal average is helper function that takes in a list of numbers num and it calculates the average of numbers within the list. Notice that we've added time.sleep before each line. Extra checking is added tip area. This is where we'll write sequential program. Oh, the sequential approach that we did like way at the beginning. I don't even think we did a sequential example. It was just kind of, this is how you've always done it type beat. Average calculates the average of 3 lists. calculate average. Multiprocessing. So the way that I would do it is first I'd say so it creates average I just don't know what to name it. You can just call it list. We'll just call it monkey list. Oh shit. It's not gonna like that if I'm in Python 3. I don't know if that's exactly how they wanted me to do it, but that's how I would have done it, to be honest. And now it just doesn't even print it. I guess we would print it out instead. Print. Okay, there we go. I have no idea how I was supposed to estimate it. Let's see what they did in sequential. They didn't want the actual average of all three lists. Okay. Okay, now it's time to calculate the average async. In the main function, create a variable called tasks and assign it. Main async is right here. So we'll use called tasks. A list of list 1, list 2, list 3. And then assign it to a list that contains the 3 functions and using. I see, okay. So we do wrap it in this by doing cal average async Run each task concurrently, you'll need to use the await. Yeah, I just don't. Unpacks. So tasks is equal to that. Await. Is this really how they do it? I just need to see. Yep. Cool. Threading approach. Do the following in main threading. Main async, main threading. Okay. So in main threading, it wants me to create a variable called lists equal to containing 3 elements, list 1, list 2, and list 3. Create an empty list called threads. Create a for loop for I in range length lists. Create a thread called x. X is equal to threading dot thread. Target is equal to cal average. Args is equal to the tuple of lists at that index. Then threads dot append x dot start. Next, create another for loop for x in threads x dot join. Oh, I had it right. What's the question? Ended up doing good. Nice, cool, worked out. Multi-processing approach. This is the last one, right? So we have multi-processing. It's going to be very similar to the threading approach. So multi-processing, create a lists is equal to a list of list 1, list 2, and list 3. Then it's going to want me to create an empty. Create an object for list with lists. Still within main processing, create a process object for each list within lists. P is equal to multi dot process. So we created a process object with the target being, I assume, equal to calc average, and then the args being equal to lists. I'm not sure why I did it differently here, but we all have to do for I in range length lists And then one iteration should go through the process and spawn each one using the starting method. Yep, so then we can just do a p.start. Then it wants me to do a for loop. So yeah, it wants me to, okay. It wants me to do basically the same thing, but we'll just have a thing called processes is equal to the empty list. Processes dot append with p for p and processes p dot join. Let me check main. So they first created a lists, and then they did list comprehension. I see. So they didn't do this. They just did another for loop, so for p and processes p dot start. So let's read the list comprehension once to see. So it's process target cal average lists x for x in range length list. So for x in range length lists, it's going to do multi-processing for that's basically what I have. No, so for I in range length lists, p is equal to multi-processing dot process multi-process. What is it called? It's just importing process. So we can just do, instead of this, we can just do process, right? Because for some reason it didn't just import multiprocessing, it said from a multiprocessing import. I didn't check that originally. Let's see what happens now. All the other ones should work identical. Nice. They all loaded, which is perfect. Exactly what we want to see. And that's going to actually do it for this video. We have deployment, which is talking about installing Flask, which is something that if you are interested in, we can do, but that's going to actually do it for the multiprocessing unit here. In the next video, obviously, we're going to start with some bash scripting, if that wasn't very obvious when we loaded up this new kernel or whatever. But yeah, that was it. We finished concurrent programming in Python. That was a pretty fun and longer video. If you did enjoy, please be sure to leave a like, subscribe, and I will see you in the next one. Peace out.